To our session of online Pegasus office hours. Today we have George Papadimitriou from our group at ISI, who has been working on enabling Pegasus workflows on OLCF resources such as Summit. A thing different which he has looked into recently is trying to get a workflow submission node up and running within the Kubernetes cluster that OLCF provides. So I'll hand over the mic to George and let him take the office hours forward.
Thank you, Karan. So basically, today I'm going to talk about our Pegasus workflow submit node deployments on OLCF that are using Kubernetes, are able to submit jobs to Summit, and the rest of the systems that they have there. So the outline for the presentation is basically a brief introduction to Kubernetes, and I'm going to talk about some basic code concepts that we're going to use and reference during the presentation. But I want to make clear that this presentation is definitely not a Kubernetes presentation, and I'm not an expert on Kubernetes. So we're going to cover basic stuff just to understand the deployment. Also, we're going to talk about how to deploy this Pegasus submit nodes, and also I'm going to give a brief hands-on demo of like a very simple workflow that we have set up running on Summit. So before I begin, I want to thank Jason Kinsel, Valentine Ananthurat, and Jack Wells, the people at OLCF that helped us get this running, and also gave us access to their Openshift cluster to introduce this opportunity for Pegasus. So yeah, let's begin. So Kubernetes, what is it and why it's so hot lately? So basically, Kubernetes is an open source platform that allows us to run and coordinate containerized applications across a cluster of machines. And this can be useful for orchestrating containers, control and automate the deployments that we have, scale container applications on the fly, and more stuff. Some key objects within this architecture is a master node, which controls the Kubernetes nodes and assigned tasks. The nodes themselves, the actual hosts, which perform the assigned tasks. Then we have the notion of pods, which is a group of one or more containers that are deployed on a single node. We have our application controller that controls how many copies of a pod we are running on our cluster. Services, these allow pods to be reached from the outside world, and also the kubelet that's responsible for spawning the tasks on the nodes. On the right side, you can see like a small abstract of what Kubernetes is, and you can see that we have the master that has Kubernetes on top and runs on top of the host OS, and then on the nodes you have multiple pods running, and Docker is spawning these pods. And you have the host controlling everything else. And also in the slides for the Kubernetes, I have references to the documentation, so you can take a look and dive in the details more. So as I said, we're not going to cover very in depth the Kubernetes deployments. But we're going to cover three things. One is how we configure objects and resources within the Kubernetes. And we're going to talk about the pods, and we're also going to talk about services. So about configuring objects, Kubernetes, they support specification files. And with these files, we can basically describe what applications we want to run, which services we want to expose, and which other objects we want to have deployed. So these specification files come in YAML and JSON, And an example you can see on the right side. This is a YAML example that spawns a pod. And as you can see, it has some metadata. And afterwards, they have some specification, for example, which container to run, how much memory and how many cores you want to have, and also the arguments for this container. For the pods, so what is a pod? A pod is considered to be like the basic execution unit of the Kubernetes application, and it actually represents a process running on the cluster. So as I said, pods can have one or multiple containers running within a pod, and when you have multiple containers running within a pod, they actually share the same resources, and also they have access to the same files and storage without you attaching a volume, for example. Additionally, pods have also their own networking, and each pod is assigned a unique IP address within the cluster. And if other pods want to communicate with each other, they have to go through that IP. But containers running within the same pod, they can communicate with each other via the localhost. Additionally, storage, a pod can specify a set of shared storage volumes, and you can have multiple pods sharing the same storage resources. And actually, this is good because you can have persistent data that way. So basically, volumes persist data, and that allows pods to maintain state between restarts. Finally, the life cycle of a pod. So a pod starts running on its assigned cluster node until the containers running on the pod exit, or if it is removed for some reason. For example, the user may delete the resource. So this is a very brief description, and you can find way more on the references on the Kubernetes website. Also, if I'm going too fast, please feel free to interrupt me and I can explain more. Third thing we're going to talk about is the services. So a service, as I said, provides an abstract way to expose an application running on a set of pods as a network service to the rest of the world. So since pods are ephemeral, services allow users to access the backend applications via a common way. So you can think of the service as a proxy to your cluster, and then messages and packets are getting forwarded to the right resources. So services have 4 types, and they can be cluster IP, which is the default one and exposes the service on a cluster internal IP. You can have node ports. These type of services expose the service on its node's IP at a static port. We can have load balancers that expose the service externally and load balances it, and external name, which is similar to a CNAME record. For our deployment, we're gonna use the node port. So in our specifications, you're gonna see that we have a service spawned, and it specifies a type as node port. So Kubernetes at OLCF. At OLCF, they have deployed Openshift, which is a distribution of Kubernetes made by Red Hat. And Openshift provides both a command line and a web interface to manage your Kubernetes objects, like pods, deployments, services, storage, etc. OLCF deployment has an automation mechanism as well built in that allows the services to interact with the batch system and access the shared file systems, such as the NFS and the GPFS that exist within the OLCF. Finally, all containers that run within the Openshift cluster, they are running under an automation user that is tied to your project. For example, if you have a project named CSC355, you'll also have an automation user named CSC355_A user. Jason Kinsel gave a presentation about this deployment at OLCF, and you can find his presentation in this PDF here on the bottom side. So this is our layout and how our deployment looks like, and it's colorful. I'm going to start explaining each thing from the left to the right. So basically, in our deployment, we have users that can reside outside the OLCF demilitarized zone, so they don't have direct access to the resources, and they can authenticate themselves on the Openshift cluster, and they can acquire secure tokens to interact with the resources on the Openshift cluster. So basically, a user connects to the Openshift cluster, and it can spawn services there based on the images that he has built. So within the Openshift cluster, what we do for Pegasus is that we spawn a container having both Pegasus and HD Condor. And that's because HD Condor is a dependency for Pegasus. Additionally, we spawn a Pegasus submit service that exposes the HD Condor grid manager service to the outside world. And when I say outside world here, I mean within the rest of the OLCF infrastructure, because everything else is pretty much blocked to the outside. Afterwards, what we do is that we can submit jobs to Summit and RIA, but this has to happen from the DTNs. So on the DTNs, we installed HD Condor Bosco, and this allows us to do SSH-style submissions. So the OLCF folks, they have introduced an automation, and basically they can give us passwordless SSHs to the DTNs for the automation users. And this is the road we take to do the submissions. We SSH to the DTNs, and using HD Condor Bosco, we convert the Pegasus Condor descriptions to LSF or SLARM descriptions, and we can submit to Summit and RIA. Additionally, on the DTNs, because we want to have two-way communication with our submit pod, there is a process called socket, and this is getting executed so we can have remote port forwarding to our submit pod and allow HD Condor Bosco to interact with the Pegasus submit pod and the HD Condor grid manager. So basically, this takes care of the submission through to Summit and RIA, and also in order to have a consistent state between jobs, and also if something happens to the pod, we're using the Alpine file system and the NFS home in order to save our files and run our workflows from there. So basically, all the files for a workflow are getting generated on the Alpine file system, and all the executables for a workflow can either be saved on the NFS home or the Alpine file system. This allows us to create the necessary rescue DAG files that we have. So if something happens, they will still be there, and you can restart your workflows from the point they failed, or from the point the Openshift cluster killed your pod. Are there any questions regarding that? Okay, moving on. So what are the advantages of this deployment? First of all, we can create environments at OLCF within a couple of seconds, and that simplifies a lot the deployment. We have HD Condor Bosco SSH style submissions, and this is versatile enough to allow us to use the DTNs, to use RIA with SLARM, and to use Summit with LSF path schedulers. And additionally, because we have cross-submission enabled within the OLCF infrastructure, we can use within one workflow the DTNs to do transfers. We can use Summit to do some heavy processing or heavy simulation, And then we can take the lightweight processing on RIA. And this can happen within the same workflow and within the same specifications of that workflow with Pegasus. So if there are no questions regarding the deployment, I can explain how we deploy this. So for the deployment tutorial, we already have this on our website, and pretty much I'm gonna be following the steps that already exist in the tutorial. So if you click the link, you can go there and find it yourself. And if you have access to the OLCF, you can also follow that later. So for the deployment, we have some prerequisites. And the first one is that you need to download the Pegasus Kubernetes templates that we have created for the OLCF deployment. And you can find them on our public GitHub repository. Also, you need the Openshift's origin client. And this client is used to authenticate yourself against the Kubernetes Openshift cluster to OLCF. And you can use it to create resources, to create container images, and it's basically the way you interact with the Openshift cluster. Additionally, you need a working RSA token to access the OLCF systems. And of course, you need to have an automation user. And finally, you need to have an allocation on the Openshift cluster. So quick note here. At OLCF, they have two clusters. One is Marble, and the other one is called Onyx. The one we are interested in is Marble because it's the one that has access to the POD schedulers and Summit. So this is the one we're using. So a couple useful client commands that you can use with the origin client. So the binary for the origin client is called OC. And with the OC login command, you can acquire access tokens and authenticate yourself against the cluster. With the OC status, you can get the status of your deployments within that cluster. The OC describe command, it will give you back details for a specific resource. With the OC create, you are able to create Kubernetes resources based on specification files. For example, YAML files. With the OC start build, you can start building a new container image. With the OC logs command, you can retrieve back logs for a Kubernetes resource, and this is very useful for debugging. The OC exec executes a command within a container. And with the OC delete, you can basically delete resources that you have created before. So in our GitHub repository for the Pegasus Kubernetes deployment, we have some templates. And these templates, we can basically break them down into 4 files. One is the bootstrap, and this is used to customize the Docker files and the Kubernetes pod, service, and build specifications for your deployment. The Pegasus Submit build configuration file, which creates a build configuration for your container image. A Pegasus Submit service, that's the one that contains the specification for exposing the grid manager service running within your pod. And also the Pegasus Submit pod. It's the Kubernetes pod specification that is used to create the Pegasus Condor pod with access to the GPFS file system and the POD schedulers. So the first thing that you need to do before start doing anything else is basically customize the templates. And what you need to do is that you can open up the bootstrap.sh file and replace the user section, the user ID section, the user group section, and the user group ID section. And finally, the grid manager service port with your specific information. For example, If your automation user is named CSC001_A user, you need to replace that within the quotes. Same with the user ID for your automation user and the user group for your group. For example, if your project is named after CSC001, that's also your group. And also your group ID is the group ID referencing that specific project. Finally, for the grid manager service port, you need to pick a random port between the range of 30,000 and 32,767. And that's because the Openshift cluster is only using this range of ports for the node port services. After you've edited this file, you can run the bootstrap.sh, and it will create your customized scripts for the Kubernetes deployments. So these scripts, the templates that we have, you can find them within the templates folder in the GitHub repository. And afterwards, after you run the script, the bootstrap.sh, the templates will be customized, and they will end up in the Docker folder as a Docker file and in the specs folder. And you will see 3 files here, one for the container build, one for the service, and one for the pod. So, first step that you have to do in order to deploy your Pegasus Submit node is to log in and authenticate yourself against the Marble cluster. And the command you have to use is the OC login followed by -u and your username, and also the URL of the cluster. In order to authenticate, you use the password that you usually use to authenticate yourself for OLCF resources. So if you have an RSA token, you use your password, and no matter what's the RSA token or just the RSA token, if this is allowed. Secondly, you have to build the container image. So building a container image comes in 2 steps. First, we have to create a build config, and basically this says to the Openshift cluster that, hey, I want to create a container image, and this is the configuration for the build. And afterwards, you can start the build by doing oc start-build, giving the name of the build, and also the Docker file that you want to use as a reference to build the image. While building the image, it can take a while, approximately 20 to 30 minutes. However, you can always follow the progress of the build by using the OC logs command, and you can do OC logs-f and give the name of your build, and it will give you back a trace that updates as the file updates, as the log file updates. And you can see if something goes wrong, you can basically stop the build and restart it, or remove the entire build, and basically act before you finish the image, before you finish building the image. Also, this is a good way to verify that your image has been built correctly and that all your executables have been included within the image. After we've built the image, then we're good to go. We can first start our service, and in order to create the service, we use again the OC create command that creates a resource, but now we give a different specification file. We will give the specs/pegasus-submit-service YAML file, and this describes our htconda grid manager service. So let me show you how this YAML file looks like. For our deployment, I've already run the bootstrap to the states, so I'm gonna go to specs, and I'm gonna open the Pegasus submit the service YAML. So it's a pretty simple YAML file. It basically defines a name for the service, and it also gives a label for the service. And we define the port, we define the type as node port, and afterwards we also define the service name and the port that we want to redirect the service to our containers, which is the 11,000, and also the node port that corresponds to that service. In our configuration, I've specified 32753, but this can be any port within the range I already mentioned. So in case the creation of the service fails with a message that says the port is already in use and you cannot use that port, you can go back to the bootstrap.sh, change the port to a different number, and rerun the bootstrap datastates. This will create again the files that we want for the Kubernetes deployment, but you don't have to rebuild the container because the container is not built with the port hard coded. So basically, you can skip the container creation and just resume from step 3. Step 4, after we have our container, we can start our, after we have our service running, we can start our pod with Pegasus init conda. Again, we're using the OC create command, and this time we're giving a different specification file, which specifies the pod creation with the image that we've built before in step 2. Sorry. So this YAML file is a bit longer than the previous file, but still small in size. And some key points here that you have to pay attention is that in the annotation section, we're using 2 of the triggers and automation hooks that the OLCF people offer. And one of them is the batch scheduler hook. And this allows the pod to receive SSH keys for submissions to Summit and RIA. And also the file system hook that tells the pod to attach NFS and the Alpine file system. In the container specification, you'll see we provide the image that we've built before within the Docker registry of the Openshift cluster. And additionally, in order to use the grid manager service address with our customized port, we're just using an environmental variable that it's getting exposed within the container. Optionally, you can also define limits for your pod. And here I have defined 2 CPUs and 2 gigs of RAM. And this is also the hard limit because I request 2 and 2 gigabytes in the first place. So after you create the pod, you can also log on. to set up the environment. Sorry, hello. Karan, are you there?
Yeah.
Did something happen to the recording?
No, like Blue Jeans was in between lost their networking. So we
Okay,
just
okay.
work back.
Yeah, we had the network glitch at ISI.
Okay. So yeah, step 5, sorry for the interruption. So step 5 is optional, and it needs to happen only the first time you bring up your Pegasus workflow submit node inside the Kubernetes cluster at OLCF. And you have to execute the remote postcode setup.sh script that exists within the pod. So basically, in the cell we got on the previous step using the OC exec command, we have to execute this bus script. And this bus script, what it does, it connects to the DTNs and creates the environment there for the Bosco SSH submissions. Basically, it installs HD Condor Bosco on the DTNs under your account, under your automation user's account, and additionally installs some scripts that we need for LSF and Slurm submissions.
George, we cannot see your screen any longer.
I'm sorry. Wait. Can you see my screen now?
Yep.
Yeah, so let me repeat one more time. So step 5 is optional, and you have to execute the bus, the /op/remote_bosco_setup.sh script only the first time you create your pod. And this script installs files on the DTNs that we need for the submission to RIA and Summit and the DTNs. After you've done with everything, you can exit the interactive terminal you already got within the pod, and you can check the status of your deployment by using OC status. And this will give you back a similar message like the one below. Basically, we have a service running, and on that service, we have attached a pod. And also, we have a build configuration that we've built our image with. Finally, if you want to clear your environment, you can delete your pod, you can delete your service, and you can delete your container and image build configuration by using the OC delete command. And based on the names we've given to the services and the pods, we can delete the pod by using OC delete pod Pegasus.submit, OC delete service Pegasus.submit.service, and you can delete the container by using OC delete build configuration Pegasus.OLCF. Are there any questions regarding the deployment? Okay, so the last thing in our presentation today is a demo workflow. And I'm going to run a workflow that we've included in our tutorial, and it's the Diamond workflow that comes with the Pegasus distribution as an example. Is the terminal visible enough? Should I increase the font, or is it okay?
You need to increase it a bit so that it becomes a bit more bolder. Yeah, perfect.
Okay. So I've already authenticated myself using the OC login command, so I'm not going to run it again. And if I run OC status, I already have a pod and a service running. So I'm going to take them down and restart them again. So we're going to use the OC delete command to delete the pod. Running again the OC status, and you can see the pod is gone and just the service is up. I'm also going to delete the service just to start fresh. And now the service should be gone. The only thing that's left is the build configuration, which I'm not going to delete. I'm going to keep it that way because it takes a while to rebuild the image. So, starting fresh, I'm going to create the service first with the OC create command, and I'm going to give the argument for the service specification, which is Pegasus submit service YAML. And this brings up the service to expose the grid monitor. You can see it's up. Second step, I'm gonna create our pod with Pegasus, and this is done again with the create command. But this time I'm gonna give the pod specification as input. And this acquires resources and brings up the pod. So you can see the pod attached to the service. However, it takes a couple seconds to get the pod initiated and get it running on the Kubernetes cluster. So let's try to get an interactive terminal to the pod. We're using the OC exec command with the IT arguments. We're giving the name of the pod, which is Pegasus.submit, and also the command we want to run, which is spin bus for our case. So we can get a bus terminal, bus cell back to us. And as you can see, now I've got an interactive cell within our pod on the Openshift cluster. So now what I advise people to do is, instead of running on your local home directory of the pod, because if you see here, it's just like /home/csc355_user. This is a local home directory within the pod, and this space is ephemeral. If you save data here or files or whatever, they're going to be lost by the time you delete the pod. So what you should do is you should switch directories to your Scratch directory in the Alpine GPFS file system. And you can change your project. Our project is CSC355, so I'm going to change to that one. And we have a Scratch directory, and we have a directory for our automation user. So this is the place you probably need to save your files in order to protect them from getting lost between restarts. And because it's Scratch, if you want to save files permanently, you probably should move them to a more permanent area, like your CCS NFS folder. So I'm gonna remove the tutorial folder that I've created before and create a new one. I'm gonna switch to that directory, and now I'm gonna use the Pegasus init command. The Pegasus init command is a script that can be used to generate skeletons for specific machines, and it can give you examples so that you can run against those machines. So by running Pegasus init, you need to provide also a folder for your workflow that you are going to create. And I'm going to call it Diamond. And it asks you whether it's a workflow tutorial. Yes. And then it asks you for which system is this workflow. You'll see that the eighth option here is OLCF Summit, and it's configured with POSCO, so this is the one we're going to use. And afterwards, it asks you for your project within the OLCF. Our project is CSC 355. And you can see a group of workflows that you can create as examples. And as I said, for this one, we're going to use the diamond example. So after this step, you've created a demo workflow within your account. And you will see that we have a folder called Diamond. And if you change to that directory, you'll see the files that Pegasus generated for the specific site. Before we generate the workflow, let's take a look in some of the key files for Pegasus. One of them is pegasus.properties. And in this file, apart from specifying the sites catalogs, the file catalogs, and the transformation catalog, we have to specify the data configuration. And because we want to run against Summit, we're using the shared FS configuration for our data. And this is the most important attribute in this file, because if we don't use the shared FS, then the default one is Condor.io, and this won't work against Summit. And also the non-shared FS, you have to do some extra steps to make it work. So let's use the shared FS for simplicity. Additionally, one more thing that you need to take a look at is the sites.xml. And here you can see two sites specified. One is the local one, and we're using as a shared scratch for Pegasus a location in the GPFS Alpine file system. And also the shared storage is again on the GPFS Alpine file system. So both scratch and output will go to the Alpine file system. Further down, you'll see another site which is for Summit specific, and it has two grid arguments. The first one is for the auxiliary jobs, which can be folder creations, file transfers, etc. And we instruct Pegasus and Condor to use the DTNs and the LSF scheduler to do these operations. In the same way, we're using same description we're using for the compute jobs. Again, DTNs will be used, and the LSF scheduler will be used for the compute jobs as well. We have also specified our shared scratch within the Alpine file system, and it's the same scratch folder as the local site description. And we're going to use the Pegasus style submission as SSH. Another thing is that we're using the batch queue on Summit to do the submissions for the compute jobs. And we instruct Pegasus to use our pod, like the workflow submit node, for the transfers, because we have attached the NFS and the Alpine file system. So our pod has access to all the files that the compute nodes have access to. And it's basically faster and easier to do these operations through the workflow submit node. In order to have successful submissions to Summit, we have to specify three keys in the Pegasus namespace. One of them is the runtime, because you cannot submit LSF patches without a runtime. We specify the nodes, because you have to specify how many nodes you want to request for a compute job, and also the project. You have to specify the project that the compute job needs to be run with. So these are the most interesting things that you have to take a look at. But apart from that, the rest of them is very simple. The replica catalog contains just one file that we're going to process, and the transformation catalog has a location of our scripts that we're using for this workflow. All right, so let's generate a workflow. And I'm going to name the DAX diamond.dax. And now we have a new file generated, diamond.dax, that creates the Pegasus generated workflow. And I'm going to run it in a cluster mode. We can watch the submission, the progress of the workflow by using the Pegasus status command. And we see that the workflow has started. And now we're running an auxiliary job which runs within the container, creating a folder. And now we've submitted our first compute job. So if we give it a couple of seconds, this job will register against the Summit's scheduler. And you can basically see that the job has submitted as well if you use the bjobs command with your automation user. And we have a job that has just been submitted, and it's still in pending stages. So let's keep watching the Pegasus run here. You have two ways of observing your jobs. You can either use the Pegasus status command, and this will give you back the output from the HD Condor submissions, or you can poll over the bjobs command, and it will give you the status of your job within the LSF scheduler. There's a slight delay in terms of how often Condor gets a status from the LSF scheduler. So changing status on the LSF scheduler is not instant on the HD Condor output, and there is a delay of 30 to 60 seconds. Okay, while we wait for the job to run, if there are any questions, I can answer.
This is Scott. I had a question.
Yeah.
So I'm wondering how long you can run the container instances for. Because I assume that's an OLCF policy. Is it like, I don't know, 6 hours a day, 2 days, as long as you want?
So as far as I know, there's no OLCF policy restriction on the pods. You have certain resources that you can use, certain limits. For example, our project has a 4 CPU allocation with 4 gigabytes of RAM, I think. So you can use these resources for as long as you want. Also,
yeah,
I think
this is Val from OLCF.
Yeah.
Time-wise, I mean, these pods can be persistent, but when the problem is that when there is a scheduled maintenance of the file system going down, so you have to handle all those exceptions. And then if you want to make the pod persistent, that's not a problem.
Okay, great. Yeah, I was thinking from the perspective of long-running workflows, and obviously that's easier if you aren't having to, restart things every day or two. So, thanks.
No, I mean, you just need to be able to watch and handle, say, if the systems are down for maintenance or the file system doesn't become available or doesn't become responsive, you need to work around that.
Mm-hmm. So quick note on this one. We haven't worked on restarting workflows automatically with the pods. This has to happen like via an actual human logging in, but we will have the checkpoints and you can continue from there. And probably it's a next step, like a next refinement that we have to do with this deployment to be able to continue even if there is an error in the pod, if something happens to the pod. So the job is now running on one of the nodes on OLCF, and you can get more information about the job if you use the bjob.cell. And you can also see that the job is running in the Pegasus status output. Any other questions regarding the deployment while we wait?
Hey George, one question.
Yeah.
Do you have access to burst buffer when you use Summit node? Does the OLCF Kubernetes cluster has access to this?
So the burst buffers are only for the compute nodes. The Kubernetes cluster doesn't have access to it, but if you submit a job to the burst buffers, then you will be able to have access. And if Val wants to comment on that, maybe he knows more.
Yeah, so it's only for the compute jobs. So,
yeah, so if your job is using the burst buffer and you submit it via your deployment, it will work?
Yes.
Okay, cool, thanks.
But you will
and you'll access to it only when the job starts running.
Yeah, I know. I tried once.
And you will still have to transfer your data in during like your job, the start of the job, like before the job runs.
Sure.
So the workflow is complete, and if we do Pegasus status submit, we can say it was successful. So yeah, this concludes the demo that we were planning to do. This project, this work was done under the Panorama 360, and of course in collaboration with OLCF. And again, I want to thank Jason Kinsel, Valentine, that's on the call, and also Jack Wells for allowing us to use their Openshift cluster and make this deployment happen. If there are any questions, I can answer them now, or if you have questions later, feel free to email us, and we will respond to them as soon as possible.
Nice talk. Thank you, George.
Yeah.
Thanks, Val, for joining.
Yeah. So with this, if there are no more questions, we'll bring our office hours to an end. Thank you, George, for conducting an awesome office hours and being right on time. All right. Goodbye. Have a good weekend.
Thanks.